There is a stone in Lebanon that weighs more than 4 jumbo jets fully loaded with passengers, cargo and fuel. It sits partially embedded in bedrock at the edge of an ancient quarry, approximately 1 kilometre from a ruined temple complex on a plateau overlooking the Beeka Valley. The block measures 19.6 meters in length, 6 meters in width, and 5.5 meters in height. By volume alone, it represents over 1,000 cubic meters of solid limestone. Geologists who have examined the stone confirm it was shaped deliberately. The surfaces are flat, the edges are squared. Tool marks remain visible along its length, indicating it was cut from the surrounding rock face using techniques that left consistent horizontal striations. The block was never moved from its quarry. It remains exactly where it was carved, lying at a slight angle with one end still attached to the bedrock beneath it. The current weight estimate places it at approximately 1,650 tons. For context, that is heavier than any object moved by modern construction equipment. The largest mobile cranes in operation today are rated to lift around 2,000 tons, but only under controlled conditions with stabilized ground, engineered support structures, and lifting points specifically designed into the load. This stone has none of those features. It is a single piece of limestone, shaped thousands of years ago, abandoned in place. 1 kilometer to the west, inside the ancient complex now called Baalbek, 3 similar stones sit in a row, perfectly fitted into the foundation of what was once a Roman temple. Each weighs approximately 800 tons. They are placed side by side with almost no visible gaps, forming a continuous section of wall more than 60 meters above the valley floor. No mortar binds them, no clamps hold them. They simply rest there, locked in position by mass and precision. Archaeologists currently attribute the Roman sections of the temple to the reign of Emperor Augustus, beginning around 15 BCE. But the massive foundation stones, the ones weighing 800 tons each, are different. Their construction style does not match Roman engineering methods. Their placement predates the visible Roman structure, and the quarrying technique used to produce them remains difficult to identify. Conventional history explains Baalbek as a Roman construction project built on earlier Phoenician ruins. The timeline places most of the visible temple work between the 1st and 3rd centuries CE. The foundation stones are assumed to have been laid by earlier cultures, possibly Phoenician, possibly Persian, possibly older, but no surviving records describe their construction. No inscriptions credit their placement, and no engineer has successfully demonstrated how stones of this mass could have been moved from the quarry to the construction site using technology known to have existed in the ancient world. This is not a mystery of interpretation, it is a problem of physics. According to conventional history, Baalbek began as a Phoenician religious site dedicated to the storm god Baal. The name Baalbek itself derives from this association, meaning Lord of the Beeka. The location was strategic. The plateau sits at an elevation of approximately 1,150 meters, commanding views of the valley below and providing access to trade routes connecting the Mediterranean coast to the interior. When Alexander the Great conquered the region in 334 BCE, Greek influence transformed the site. The Phoenician deity was reinterpreted as Helios, the sun god. Later, after the Roman conquest of the region in 64 BCE, the site was renamed Heliopolis and incorporated into the expanding Roman religious infrastructure. The Romans began construction of a massive temple complex dedicated to Jupiter, along with smaller temples honoring Bacchus and Venus. These structures remain partially intact today and are among the largest Roman religious buildings ever constructed. Researchers generally agree that the Roman construction occurred in phases. The earliest work, including the grand courtyard and the foundations for the Temple of Jupiter, likely began during the reign of Augustus and continued through the 1st century CE. The columns of the Jupiter Temple, 6 of which still stand, are among the tallest in the Roman world, reaching 22 meters in height with a diameter exceeding 2 meters at the base. But beneath the Roman columns and above the natural bedrock lies something different. A massive stone platform constructed from blocks far larger than anything the Romans typically used. These blocks form what is known as the trilithon, a section of the western wall comprising 3 enormous stones, each weighing approximately 800 tons, placed horizontally in a row. Above them sit 3 additional courses of smaller but still substantial blocks, some weighing 50 to 100 tons each. Mainstream scholarship attributes the trilithon to an earlier phase of construction, predating the Roman work but post-dating the Phoenician presence. The current consensus places this phase somewhere between the Hellenistic period and the early Roman occupation, roughly between 300 BCE and 100 CE. The stones are assumed to have been quarried locally and transported to the construction site using methods consistent with ancient engineering capabilities. This explanation relies on several assumptions. First, that the stones were moved using sledges, rollers, and large teams of workers. Second, that wooden ramps or earthen embankments provided the necessary elevation to place the blocks 60 meters above the valley floor. Third, that the workforce available during the Hellenistic or early Roman period was large enough and organized enough to sustain such a project. And fourth, that the tools available at the time, primarily bronze and iron implements, were sufficient to quarry, shape, and finish stones of this mass and precision. Each of these assumptions is plausible in isolation. Together, they form a framework that has guided scholarly interpretation for more than a century. But the framework has never been tested against the physical constraints the project would have imposed. No modern engineer has successfully demonstrated how 800-ton blocks could be moved 1 kilometer across uneven terrain using ancient technology. No reconstruction has shown how such blocks could be lifted 60 meters and placed with millimeter-level precision. The explanation remains theoretical, supported by analogy to other ancient construction projects, but not by reproducible demonstration. The logistics begin with the quarry. The limestone used for the trilithon and the larger unfinished block was extracted from a site approximately 1 kilometer south of the temple complex. The stone lies in a natural bed, relatively close to the surface, which would have made initial access straightforward. But extracting blocks of this size from bedrock is a different challenge. Modern quarrying of large stones uses diamond wire saws, hydraulic splitters, and explosives to separate material from the parent rock. Ancient quarries show evidence of a different technique. Workers carved channels around the perimeter of the intended block, creating a trench deep enough to allow access beneath. Wooden wedges soaked in water were driven into the channels, expanding as they absorbed moisture and gradually splitting the stone free. Alternatively, metal wedges were hammered into pre-cut slots, applying controlled force to fracture the rock along desired lines. These methods work for blocks weighing a few tons. They become exponentially more difficult as mass increases. An 800-ton block requires a perimeter trench several meters deep, cut entirely by hand. The labor involved would be measured in months, possibly years, depending on the workforce size and the hardness of the stone. And once the block is separated from the bedrock, it must be moved. The distance from the quarry to the temple site is approximately 1 kilometer, but the terrain is not flat. The route includes a gradual upward slope of roughly 60 meters in elevation. Moving an 800-ton object across this distance would require a transport system capable of handling not only the mass, but also the friction, the incline, and the uneven surface conditions. The standard explanation proposes wooden sledges and rollers. A sledge would distribute the weight across a larger surface area, reducing ground pressure and preventing the block from sinking into softer soil. Rollers placed beneath the sledge would reduce friction, allowing the block to be pulled forward incrementally. Large teams of workers, potentially numbering in the thousands, would provide the pulling force using ropes. Experimental archaeology has tested this method on smaller scales. Modern researchers have successfully moved multi-ton stones using sledges and rollers, demonstrating that the basic principle works. But scaling this technique to 800 tons introduces complications that remain unresolved. The rollers themselves would need to be massive, thick wooden cylinders capable of bearing hundreds of tons without crushing. The ropes would need to be correspondingly strong, woven from materials like flax or hemp, in quantities that would require significant agricultural output. And the coordination of thousands of workers pulling in unison would require a level of organization and communication that ancient societies may or may not have possessed. Even if the transport problem could be solved, the placement problem remains. The trilithon stones sit 60 meters above the valley floor, embedded in a wall with stones both above and below them. Lifting an 800-ton block to this height would require either a ramp system of extraordinary scale or a lifting mechanism capable of handling the load. Ramps are the conventional solution. Roman engineers used earthen ramps to construct large buildings, and similar techniques are assumed to have been employed at Baalbek. But the ramp required to lift 800 tons 60 meters into the air would need to be long enough to maintain a manageable incline, likely several hundred meters in length, and wide and stable enough to support the block and its transport apparatus. The volume of earth required for such a ramp would exceed the volume of the stones being lifted. No trace of such a ramp has been found at Baalbek. Lifting mechanisms present similar challenges. Cranes and pulleys were used in Roman construction, but the largest known Roman cranes were rated for loads of 10 to 20 tons, not 800. Scaling a pulley system to handle this mass would require engineering solutions that left no archaeological trace and no written description. The absence of evidence is not evidence of absence, but it complicates the reconstruction. What remains uncertain is not whether the stones were moved, and they clearly were, but how the process was accomplished using the technology and labor available at the time. The gap between the proposed methods and the physical requirements grows wider the more closely the logistics are examined. The dating of the trilithon has been a point of contention among researchers for decades. Mainstream archaeology places the stones in the Hellenistic or early Roman period based on their integration into the larger temple complex. But some scholars have noted that the construction style of the trilithon differs significantly from Roman methods, suggesting it may predate the visible Roman work by a substantial margin. One area of disagreement centers on the tooling marks visible on the stones. Roman masonry typically shows evidence of chisel work with consistent patterns and angles. The trilithon blocks display a different surface treatment, with less regular tooling and a finishing technique that some researchers interpret as older. Proponents of an earlier date suggest the stones may have been quarried and placed during the Bronze Age or earlier, potentially as part of a pre-Phoenician structure that was later incorporated into successive building phases. This hypothesis faces methodological challenges. Direct dating of stone is difficult because limestone does not contain organic material suitable for radiocarbon analysis. Dating must rely on contextual evidence, pottery, inscriptions, or construction techniques that can be linked to known time periods. At Baalbek, the contextual evidence is sparse. The trilithon is embedded within layers of later construction, making it difficult to isolate its original placement phase. Not all researchers agree on the interpretation of the construction sequence. Some archaeologists maintain that the trilithon is contemporaneous with the Roman work, arguing that the differences in technique reflect variations in labor gangs or regional practices rather than temporal separation. Others point to the precision of the stone placement as evidence of advanced engineering knowledge, suggesting that whoever placed the trilithon had capabilities that exceeded typical Roman standards. The debate extends to the question of purpose. If the trilithon predates the Roman temple, what was it originally built to support? The stones are positioned in a way that suggests they were intended to bear significant weight, but no superstructure corresponding to the pre-Roman period has been identified. One possibility is that the trilithon was part of a fortification or platform that was later repurposed by the Romans. Another is that it served a religious function, forming the foundation of a sanctuary that was subsequently rebuilt multiple times. These interpretations remain speculative because the archaeological record at Baalbek is incomplete. Excavations at the site have been intermittent, hampered by political instability, funding limitations, and the presence of modern structures built over ancient remains. Large sections of the site have never been systematically explored, leaving gaps in the stratigraphic sequence that make definitive dating difficult. What is clear is that the trilithon does not fit comfortably into the established timeline. Its presence complicates the picture, introducing variables that conventional explanations struggle to accommodate. The question of when and by whom these stones were placed remains unresolved, not because evidence is lacking, but because the evidence available points in multiple directions. Beneath the visible temple complex at Baalbek lies a network of underground chambers and passageways that has received limited scholarly attention. These subterranean spaces are carved directly into the bedrock and appear to predate the Roman construction above them. The chambers are not uniform in size or design, suggesting they were excavated over multiple phases or served different functions. Some of the passages are narrow and low, accessible only by crawling. Others open into larger vaulted rooms with ceilings high enough to stand in. The walls show tool marks consistent with hand carving, but the depth and extent of the network have not been fully mapped. Access to these spaces is restricted, and detailed surveys have not been published in the archaeological literature. This means that any structure built at Baalbek involved not only moving massive stones above ground, but also excavating substantial volumes of bedrock below. The labor required for this work would have been significant, adding another layer of complexity to the construction timeline. The material sourcing presents a separate puzzle. While the main blocks used in the trilithon were quarried locally, some of the smaller decorative elements and columns were made from different types of stone. Granite was imported from Egypt. Marble was brought from quarries in Greece or Asia Minor. The logistics of transporting these materials over distances of hundreds or thousands of kilometers by sea and land suggest a construction project with resources and organizational capacity well beyond a local or regional effort. This raises the possibility that Baalbek was not simply a religious site, but a major cultural and political center, attracting patronage and labor from across the Roman Empire. If that is the case, the trilithon may have been part of a deliberate effort to create a monument of exceptional scale and permanence, serving as a statement of power and engineering capability. Another complication emerges from the alignment of the temple complex. The main axis of the Jupiter temple is oriented to the east, facing the rising sun. This orientation is consistent with Roman religious practice, but it also aligns with older solar traditions predating Roman occupation. Some researchers have noted that the geometry of the site incorporates ratios and proportions that appear in other ancient structures, suggesting a shared architectural language or influence. Whether this reflects intentional design or coincidental convergence remains debated. Geometric patterns that seem significant in one cultural context may arise naturally from practical construction constraints in another. Without direct evidence of a planning document or blueprint, attributing specific intent to these alignments is speculative. Patterns similar to those seen at Baalbek appear at other ancient sites across the Mediterranean and Near East. The use of massive foundation stones, the integration of subterranean chambers, and the incorporation of astronomical alignments recur in structures separated by time and geography. At Heliopolis in Egypt, the temple complex dedicated to Ra used enormous granite blocks as foundation elements. At Delphi in Greece, the Temple of Apollo was built on a terraced platform supported by polygonal masonry. At Jerusalem, the Temple Mount incorporates stones weighing several hundred tons, placed with precision comparable to Baalbek. These parallels do not necessarily indicate direct cultural contact. Different societies solving similar architectural problems may independently arrive at similar solutions, but the recurrence of these features across multiple sites reframes what we thought we understood about the distribution of engineering knowledge in the ancient world. It suggests that the capabilities demonstrated at Baalbek were not unique, but part of a broader pattern of monumental construction that spanned civilizations. The parallels extend beyond architecture to include the scale and ambition of the projects themselves. At Ollantaytambo in Peru, massive andesite blocks were quarried from a site across a river valley and transported uphill to construct a fortress and ceremonial center. Some of these blocks weigh more than 50 tons. The quarrying and transport techniques remain unclear, and no ramps or lifting devices have been identified at the site. At Sacsayhuaman, also in Peru, walls were constructed from stones weighing up to 200 tons, fitted together with such precision that no mortar was needed. The stones are irregular in shape, requiring each block to be individually shaped to match its neighbors. The labor and planning involved in this type of construction exceed what is typically associated with pre-Columbian societies in South America. At Stonehenge in England, bluestone pillars weighing several tons each were transported from quarries in Wales, more than 200 kilometers away. The largest sarsen stones, forming the outer ring, weigh up to 30 tons and were sourced from quarries closer to the site. The methods used to move and erect these stones remain incompletely understood, with experimental reconstructions demonstrating only partial success. These sites share characteristics that complicate the conventional narrative of technological development. They involve the movement of exceptionally heavy stones over difficult terrain. They demonstrate precision in placement and alignment that exceeds practical necessity. And they lack the documentary evidence that would clarify how the work was accomplished. One interpretation is that ancient societies possessed engineering knowledge and organizational capacity far greater than previously assumed. This would require revising estimates of population size, resource availability, and social complexity for multiple civilizations across different regions. It would also require accepting that techniques capable of moving hundreds of tons were developed independently in multiple locations, then apparently lost or abandoned without leaving clear traces in the archaeological record. Another interpretation is that the similarities result from shared cultural exchange, with knowledge of megalithic construction spreading through trade networks or migration patterns that have not been fully documented. This would imply a level of interaction between ancient societies that current evidence does not strongly support, but cannot definitively rule out. A third interpretation is that the parallels are coincidental, arising from universal constraints on how large stones can be moved and placed. This explanation preserves the independence of each cultural achievement, but does not account for the specific similarities in technique and scale. Discoveries once dismissed as improbable have later been confirmed through new evidence. The existence of Viking settlements in North America was doubted until archaeological excavations at Lanceau Meadows provided physical confirmation. The Antikythera mechanism, an ancient Greek analog computer, was considered too complex to be genuinely ancient until detailed analysis verified its construction date. Göbekli Tepe in Turkey, a megalithic temple complex dated to approximately 9600 BCE, overturned assumptions about when large-scale monumental construction became possible. These examples demonstrate that the limits of ancient capability are not fixed, but subject to revision as new data emerges. What seems impossible based on existing knowledge may become plausible when the knowledge base expands. The challenge is distinguishing between genuine anomalies that require rethinking established frameworks and apparent anomalies that reflect gaps in documentation rather than gaps in capability. At the center of the Baalbek mystery is a question that has not been satisfactorily answered. How were the trilithon stones moved from the quarry to the temple site and lifted into position? This is not a question of cultural significance or religious meaning. It is a purely technical problem. We can measure the stones, we can calculate their mass, we can map the distance they were moved, but we cannot reconstruct the process using the tools and techniques attributed to the builders. Modern engineering offers solutions, but those solutions rely on machinery and materials that did not exist in antiquity. Hydraulic cranes can lift hundreds of tons, but they require steel cables, diesel engines, and stabilization systems. Tracked vehicles can transport heavy loads across rough terrain, but they need paved surfaces or compacted earth. None of these technologies were available to ancient builders. Experimental attempts to replicate the transport of large stones using ancient methods have met with limited success. Researchers have moved stones weighing several tons using sledges and wooden rollers, demonstrating that the basic principle works on a small scale. But no modern team has successfully moved an 800-ton block using only materials and techniques available in the ancient world. The gap between what has been demonstrated and what would have been required remains wide. This gap does not prove that the task was impossible. It proves that our understanding of how it was accomplished is incomplete. The stones are there. They were moved. The method used to move them is not documented, and efforts to reconstruct that method based on available evidence have not produced a definitive answer. What we can measure is the precision of the stonework. The trilithon blocks are fitted together with gaps measuring less than a millimeter in some places. This level of precision requires not only accurate cutting, but also careful placement, ensuring that each block sits exactly where intended without damaging the surfaces in contact. Achieving this precision with an 800-ton object is a technical challenge, even for modern equipment. What we cannot reconstruct is the organizational structure that made such a project possible. Moving stones of this size would have required coordination among thousands of workers, sustained over months or years. The workforce would need to be fed, housed, and managed. Tools would need to be manufactured and maintained. Materials would need to be sourced and transported. The logistical complexity involved approaches that of a military campaign, yet no records describe such an effort at Baalbek. The absence of documentation does not mean the project was beyond ancient capabilities. It means that the systems and methods used to accomplish it have not been preserved in a form we can access. The result stands as evidence of what was achieved. The process remains uncertain. The trilithon stones are still there, embedded in the western wall of the temple complex, 60 meters above the valley floor. They have been there for more than 2,000 years, possibly longer. Earthquakes have struck the region multiple times, collapsing sections of the Roman columns and scattering architectural fragments across the site. The trilithon has not moved. In the quarry to the south, the unfinished block lies as it was left, one end still attached to the bedrock. Tool marks cover its surface, evidence of work interrupted or abandoned. It weighs 1,650 tons, heavier than any stone successfully moved in recorded history. Its presence confirms that whoever worked the quarry intended to move stones of this size. Whether they succeeded with other blocks, or whether the unfinished stone represents the limit of their capability, remains unknown. Modern visitors to Baalbek stand at the base of the trilithon and look up at the stones fitted above them. The scale is difficult to process. Each block is larger than a bus, longer than a semi-trailer, heavier than a loaded passenger jet, and they are stacked, one on top of another, with precision that would satisfy a modern architect. The conventional explanation for Baalbek attributes the trilithon to ancient builders using methods consistent with their time period. The evidence supporting this explanation is circumstantial, based on comparisons to other ancient projects and assumptions about available technology. No contemporary account describes the construction. No modern reconstruction has successfully demonstrated the proposed methods at the required scale. This does not mean the explanation is wrong. It means the explanation is incomplete. The gap between what we know and what we can prove is wider than the historical narrative typically acknowledges. Baalbek stands as a reminder that the past is not as settled as it appears. The stones are measurable. The distance they were moved is mappable. The precision of their placement is documentable. But the process that produced these results is not fully understood, and until it is, the trilithon will remain what it has always been, a structure that challenges the limits of what we believe ancient societies could accomplish, not because it is impossible, but because we have not yet determined how it was done. The stones do not offer answers. They offer questions, and the questions, once asked, do not leave easily.